Hi guys, it's right here. Today I'm gonna show you the new installs that I've done to the printer. Um, I'm going to put a filament sensor. I'm just gonna use a switch and a pipe, and I'll show you the LED I've installed. These are the status LED, the red, blue, and green. Still haven't installed them yet. Have other status light here at the bottom. Sorry for that. Added two white status lights for illuminating the workpiece. These are the red, blue, and green. I want to add another piece, another set here, and then I'm gonna add these two. These are for the bed. I'm gonna put them there at the bottom, somewhere around here. Should be sitting somewhere like that. For the yellow lights, I'm gonna, since the Marlin firmware doesn't support yellow, only supports red, green, and blue, and white, yeah. I think I might couple this yellow with the white ones for setters. The red is for temperature when the bed, when the bed and the nozzle, but mostly it's checking the bed. There's no separate setup for the nozzle. It's just for the bed alone. So even this and this one, this one's here at the bottom, will be displaying the same status. I've soldered the negatives so that to reduce the number of wires, same as here, the sharing and negative. Done the same for the white ones, so I may just cut here and put it here, but still a wire, so I might just run the whole of it. And then here's the filament sensor. Yeah, it's stuck up a little bit, so it's closing the wire. There's one that I had made earlier. This is a filament sensor. It's a switch. It's a 3-pin switch. I'm not sure if it has an LED. I haven't tested out this switch yet. But since it's 3-pin, it should have an LED. So just hot glued it there. You can see I've bent the switch, the metallic switch, slightly down so that it touches. The thing is so sensitive, it can senses even where did I put that jig? The jig for holding. Give me a minute. Cheese. Oops, sorry for the mess. It's currently so the filament sensor is sensitive, but it can sense. This is a soldering one. You can see the tolerance is that. Just clicks. It has become slightly insensitive. It's okay. It's no let me hook it up to the Marlin firmware and test it. I haven't opened up my printing material yet because obviously because of the moisture and stuff. It's still here. I'm planning to make an enclosure for it. Sorry for that. The pipe, I'll stick the pipe here. I wanted it to face the other way around. That's a mistake. I'm gonna glue it here. That's why I've extended this this thing. Originally I was using a plate. I'm still learning how to cut, so for especially this hole, this big diameter hole, and I was using, where is this girl? I was using this girl. She's known to spit out when she's known to make a big exit hole as it chucks. So yeah, broke. So I bought this. It's not the best. It's up to 20. I needed something like 22, so I kept on drilling at an angle to increase this hole. It was for this hole here. See, now I've got a better, can't even, it has integrated with the part better. So this is going to run from here till here, where I'm gonna put the enclosure. So the enclosure is gonna run somewhere around here. It's gonna sit like that. So the pipe is just to keep it dry until it goes to the head. For the weight, I haven't checked the weight yet. The whole setup is, the whole pipe rather, it's not supporting well because it might just have to run it. You can see it's 38, so I'm approximating 42 because there's some parts still. That's not that 41. Yeah, so roughly 42. Not using a direct drive. This setup ain't going for speed. Is one of my limiting factors is my threaded rods. It was a cheap alternative. I just found a guy with a lathe made my rods, but the problem with the technique that we were using what's this thing called for making screws? You just put the rod into the lathe and I don't want to call it a die, screw die, because I don't think it's a die, but it's for external screws. The problem with it, the lathe was quite old, so the spinning axis was not straight. My pipes were bent. I tried my best, so I sandwiched the threaded rods into between two flat woods and then started beating them to flatten them as I was rounding them up. It gave me it improved the straight how should I say it, the linearity of the rods. But now the problem is my rods are 1 millimeter pitch. That's really good for resolution. But the problem is that 1 millimeter pitch means more traveling, and more traveling means more. I need roughly more revolutions. And at the moment, I'm skipping. My steppers are skipping. As you can see, the threads are in the best of the threads. It's moving smoothly because I'm using it under nut. Just sandwiched a nut there so that it can't move, and then you plug it in. I've done this for the all setups, even here, even for the Y. Moves freely, but it's not as free as I was checking, trying to test for linearity. When I'm using the marlin, the speed is, I can't go past 25 millimeters per second. Past that, I'm starting to vibrate. No, not 25 was how should I say it? 25 was the average. 50 was vibrating. 40 was skipping seriously. At 30 I can run, but at 5 it was good. But at 5 now, how am I? You can't print at 5 ms. Sorry, millimeters per second. I'm waiting for an upgrade. I found cheaper rods on at Jumia. These were quick options. At that time was just on an attachment, and then there's this person with a lathe. It was, at that time it was convenient. It seemed to be convenient, but yeah, it's not that. The other improvement that I've done is this rail. It's a wardrobe rail. It's a cheap one. It's a $3 rail. At first I was running this type of linear rails, but as you know, these type of rails have 2 degrees of freedom. They have the linear, and since it's round, it can rotate. So with this is a linear rail, and you see the play is this much. You can't imagine how much with the other rotation, how much it was with the linear rail. I just ended up checking it. Even here it is. Might end up using it in another project, or planning to build a CNC, or I build another 3D printer. I might say I'm getting more. I'm coming to terms with the coding, with the firmware. I've burnt out a breadboard. I've burnt out a ramps board. I've repaired it. I even tried to make out mine, but it's incomplete. Yeah, as you saw in the other videos, how it went. But yeah, I got the new RAMs. The 1.6 are somewhere here. I got 2 of them. I just got them for you in case. But for the 1.4, I got one. If I just burn it, I'll just get another one. The 1.6 were cheap. The 1.4 wasn't. It was coming with a mega, so I just got one. 1.6, they were selling them as standalones. They were roughly at $2. No, not $2, $20. Roughly, not 20 is expensive. Let me say 17. It's roughly 1,900 something. Currency. So yeah, that's it. Apart from this filament sensor, I tried the hotend test, but now I'm having a problem. I haven't even closed the window. It should be somewhere here. As you can see, these are the thermistor readings. This code. This code is just the default code for telling you the temperature measurements for so the data you have seen is from this code. This code is just the default code. You include the library thermistor thumb, and then you initialize a value, call it thermistor. The value stores the analog port. Oh, this was the code that I was using. No, I haven't, because that analog port is not the right one. It's not. I remember. I should change that. Okay, and then the zero is for the number, the thermistor number. If you have 2 of them, 3 of them, but currently then I have one. I'm studying one, so it's 0. And then the setup part of it, you initialize the serial port communication, and then from the thermistor, this library specifically is from the, as you can even see, it's from we have configured this thermistor to configure. Let me just expand. Configurations of it. So it's using the libraries, the same libraries as Marlin firmware. What else? I saw it was sweet. Yeah, you can find it on GitHub. Can I remember the name of the? It was just at GitHub. I googled Rams thermistor something code, and then you'll just find it there. Cause the Rams, cause I'm using this code because of plus the libraries, set of libraries, because the resistance in the Rams board is 4.7, the pull-up resistor. So yeah, it matches, so it makes my work easier. From there, you are going to use initialize another value of type double called temp1, where you're going now to store the values from the analog pin. The first initialization was for the port, the pin. The other one is now for storing the value that you are having, and then you're converting it, obviously converting it from analog to temp. It's a function from the library, converts it from resistant value to your thermometer, your temperature readings. From there you have the serial.print. Obviously that's to inform us, and then the first line, second line is you're printing now the temperature value as a string, and then the third value is just spacing and then a delay. That's code. I wonder if the RAM's board, we can test it because that port before we test it. Okay, we see. Yeah, let's just test it. Let me plug this in here. Sorry guys, one of my pots, I burnt out one of my pots as I was testing the gyroscope. I need to install my Windows again. I've tried to update the BIOS to see if I can get the With the pot done, it's now to go to the coding part of it. What's up, boy? Okay. Now from there, we can start. Let me first check. I can't remember the part for. Just disconnected the keyboard. Sorry. There's a hotend. I'm looking for the. Let me go to VB first so that I can check the port for the temperature configuration. Pins, ROMs. Temp 0 pin, so it's using 13. Bed is 14. Is for the second extruder, so I need this 13. I've forgotten to set the 13. It was connected to the LED pin. It once confused me. I was thinking I made short the internal built LED pin. So I need to copy that with Flash. There are 3 somewhere. Yeah, there's a 3. Now I need a 1. There's 1. I might just use the touch screen. Can verify the code first. I was watching some guy.
This camera's going to bed.
About TIG welds.
Good night, Jane. Good night, YouTube.
It's a new video finder. Subscribe to the guy. He's teaching me a lot about TIG welds.
Okay.
And welding. I should pause that. Okay, now the code is done compiling, so we can upload it. Done uploading. Now I can start checking at the temperatures again. Oh, it's back to normal. I can start doing for this setup. This thing can be annoying at times. As in, for a whole period of time, you're giving me a whole lot of values. Okay, now since the temperature sensor is back, it's back active. I was this setup. Now this is the actual setup. On this one, the hotend test PID. My main objective for running this code is I want to find out the PID values so that I can feed it to the Marlin firmware, because the Marlin firmware it's open source, so that means the PID values that they are using for the hotend are rather they should be off. Let me turn off the touch. They should be off. They are not. They might be of not exactly not this right hotend setup that I'm planning to use. But again, it's gonna be a good find. Checking on that, let's go back to the code so that I can show you what I was planning. Now, this is the code. Static boolean true Okay, starting from here. I've declared the LED pin, internal LED pin, the fan pin, the hot end pin, this for the heater, this for the thermometer, the 13 pin, and then there's a kill pin. Obviously I've coded the kill pin just in case something, I'm testing on heat just in case. Okay, it's just a safety thing. I got it, this code, part of it is the RAMS code, test code. It's on GitHub, the RAMS 1.4 test code. It's used to basically turn all your elements on and off, from your motors to your heaters to your LEDs to your what else is plugged in, motors, heaters, switches, the end stop switches, the thermometers. It basically checks if and every component you're having runs okay. So I took part of it. So like now this part of the kill pin is part from that, the beeper, but I've disabled the beeper. I was having some stress. I was after some runs, after I did some tests, I had a feeling I might have shorted something, so I started disconnecting things. I left this code, and started commenting out everything, just let for the temperature. Where are we at? And then there's these are the PID values: proportional, integral, and derivative. And then there's a constant. Then for this setup, for my PID setup, I'm doing my there's a PID code. There's a PID code and library at GitHub, but I thought it would be much more interesting if I started investigating, or rather started testing or learning PIDs. So, and it's supposed to be simple. The first one is just the proportional. It's the actual value, how it's coming from your sensor, or the actual data you're having. Integral is now the you integrate that the value that you have. The derivative, it's I'm using the difference between it and the previous value. I'm using the basic integration and derivation formulas. I should even show you, like so you know that the integration. Let me show you. Okay, the code is somewhere here below, but I don't know if I have it on. Excuse me. I'm not really sure. It might be one of the reasons why at the moment I'm getting an error, but not with the end. I'm getting an error on the derivative part. So this is just trying my best to be like the proportion. It's just the same as the value. Sorry for that. Straight from the value, straight from the sensor. The integral, the normal formula for integration. If I can remember, this is what I remember. So, like if it's A, it's gonna be A n plus 1 over the new power plus C. Now this is the integration constant I was telling you. Here, you see. That's for integration. Derivation is just change of x over change of time. This is my basic understanding of the integration and derivation part of it. It hasn't got it complicated yet, because there are no angles, so there are no tangents. Okay. Still, at the end of the day, it's the computer that's rather it's the microprocessor that's processing the data, so I don't have to care about it. Just feeding the formula. This this is why I love programming. Just feed in the formulas and give the computer the code. It will do everything. It will do the hard part. It will do the actual digging for you. Now, so for each there's a constant. Usually there's a constant. Therefore, constant for proportionality, constant for integration, and constant for derivation. So basically, it's just multiplying each term by a constant. Each term, its integration constant, its proportional constant, and its derivation constant. Let me check if it's. I didn't do like a simple. Not sure if you can see, these are not the best of the descriptions, but basic PID controller. Start from this is the element you're controlling to control the drone, rather. Should I use for, I had one for a heater element. How did I just discard it? I used the PID for drone mouse and got tired. Seems I just drew one for there because I'm still working on like a drone somewhere. Yeah, here are the ones. Yeah, I was sure I did something. These are I was looking for methods of PID. So like the first one, he had this guy's name, Ziegler Nicholas method. It was rather complicated for me, but it's simpler. It's in the S domain. It's the first method that people use, and then there's second method. The second method was KP plant motor KD0. Can't really remember the second. I think it's supposed to be the same. The third one is where you take the values, proportional, integral, and derivative, sum them up, then you send them for processing. So you get, like, I'm getting values from my analog sensor. Instead of just feeding in the raw values, I'm taking the values from the sensor, the proportional. I'm taking the integration of the same values. I'm taking the derivative, the change of the values, and then all these values, I'm multiplying them by a constant. Should I have like a formula? Did I have a formula somewhere? I'll just note the formula down quick for you. But basically, it's just proportion. You take a proportional constant p, which in this case is 1. You are using this for, you can test them. Now this is the part of it. These are the values that you're going to play with them, because you can't play with the integral, you can't play the derivative. Those are just values. They come like that. The only thing I can just do to them, I can scale them up. I can try to tell the processor this value is big while it's not that big. You see, that's the point of the constants. So you sum them up, send them to the processor, and then you check the values again. And then these values, most of the time, since these are sensor values, you're going to map these values to an analog input. So maybe for 20 you're going to have, it's going to send 100, and then for 100 on the other side is going to send 1,000. So you see, a range of 20 to 100 is mapped out to 100 to 1,000. So with these values that you're getting in, you see, the mapped values are the ones that are being sent here. So the processor is always getting correct information. Now let me just jot that down. That guy. Don't have a black, brown, blue. So finally it's summation of from I to forgotten I to what, from 0 to n equals to k proportion left with the value of x plus k, the integral for e of x dt plus the k derivative d of t dt. So this formula, it's roughly like that, just from the same value you're just getting, integrate it, multiply it by the integration constant, then the same value and the difference, the previous value, differentiate it, and then multiply it by the differential constant. That sum is now your new value. If the sensor was reading 20, after this process it can read something else, depending on now on your scaling, how fast or how slow you want it to scale up or scale down, depending on your computer, or depending on your process. Now let me switch off. Describe the proportional. Now int target temp at this moment. I'm not really testing if this thing is working. I want to test the mechanism of it. I want to get its transfer function. The whole point of a PID, mostly if you have a PID, you have a transfer function. This is a transfer function. A transfer function, it's basically an equation that describes your system, the function of your system. A transfer function, it's a function that states, it's a ratio rather of the output to the input. If I can remember, was it input to output to input? You do output to input. Now, for example, in mostly a normal system, like in this PID, this motor, instead of it now just reading motor, it's supposed to be a transfer function. This motor, if I feed it 20 volts, 20 watts, it's going to give me 1000 RPM. If I feed it 30 watts, it's going to give me 2000 RPM. You get that process, that feedback, that system, that input output, it's what it's called a transfer function. So it's most of the time it's might look like s plus 1 over s squared plus 2s plus 1, or s over s squared plus 1, no, not s squared, or s over, no, 1 over s plus 1. Can be something, as in just varies depending on this squared. This one, another one, can be of any. Can you even, this is a second, first, the poles and the denominators, poles and just go to denominator, differentiate. I can't remember the denominator and poles right now, but this is just a transfer function in the S domain, so it's in the Laplace form. Most of the time you feed it 20 and then gives you this. So that function describing that input to output is what's called a transfer function. Now I'm trying to find now, so every system has a transfer function. May it be heating, be it a motor, just a system, any system. even a 4-bar, your 4-bar mechanism can be a transfer function. When I give it this angle at this bar, it has the other angles at the output bar. You get, it has for X inputs degrees, it has Y degrees outputs. You can get a transfer function on that. So in this case, I want to model this thing, that hotend. I want to get its transfer function. It's just a simple thing. It's not that complicated. They don't have one of the most complicated hotends. It's square. I had taken its dimension somewhere, so it's just making it simple for me to do the thermal analysis. Where did I put? Painting materials at the front. I remember. One more page. Not that one. Here. Now, now, let me try to see what I was doing here. So this is the function that I was saying. It's just a summation of the proportional integral derivative. This is the system that you're having. This is the signal, this is the hotend, actuating hot signal, and then control feedback variable rather. Now this is the thing that you have control over. This is the thing that is being controlled. So I add or remove this, I affect this, yeah, by default. This was a simple graph of just I was trying to map out hotend temps against wattage. This is watts, this temperature. So the data here, it's not accurate. It was just for me to find a simple graph to start the actual seeing what I can do. As you can see, obviously it's a what do you use to call this? It's a polygon. Not a polygon. It's a curve. Let me just call it a curve. But basically, roughly this is the normal curves for heating that we usually have. And then the heater tends to run after accumulating power such wattage. The temperature changes are slightly higher compared to when the wattages are low. The temperature changes are low. You see, it's up to just this for this much, and this for almost this much. You get roughly. So more control loops. At the end of the day, I'll simulate everything and I'll put it into MATLAB. So I'll have, if I finish my experiments, I should be having a system that can model my hotend. I don't really need now to be powering map my hotend to give me my data. I can have the data that I have. I can map out if I feed it this watts, it will give me this temperature. This wattage can get me to a maximum, as in maximum temperature of up to here. That's the part of work that I'm supposed to be doing, to map out the sensor and the hotend. Since there's I haven't found any data sheets online, so yeah, all this for the PID values. So yeah, okay. Oh, the other thing is, in my code, the Marlin firmware tends to use the bang setup. For bang, it means the PID values for the values that you're sending to the probe itself, the temperature probe, are not varying. They have two states, high and low. At low it's 0, at high it's roughly 1024. That means I basically powering it up, it's heating up. I chuck out my power, it stops heating. There's an option because it's connected to pin 13. Pin 13 is an analog pin. There's an option of feeding it power as you want, from 0, a scale of 0 to 1024. But as you can see, scaling it from 0 to 1024, it's a lot of work. And you see, at the end of the day, you just need to get to a certain temperature. If you see for bang, it will stay on until you get to temperature. Once you get to temperature, it goes off by default. It should switch off. But if you are using these analog PID values, if like these analog values that I'm feeding right now to get my stuff. Okay, this code is not using the bang. I'm going to write a code for bang setup later, because that's where the PID values will actually come from, because the Marlin family is using the bang setup. Currently, so since what I'm using, my target temperature is at 100. I'm using 100 right now. If my probe gets to, if my temperature read sensor senses 100 degrees, it cuts out power to the. It's a form of bang, but it's not really a bang. It's only bang when it's cutting off, but during the heating process, it adds up on a. It scales up on 10. It scales up by 10. It gives 10. Check the temperature. If the temperature is below standards, it adds another 10. Repeats the cycle until you get up to temperature. My theory for this was I might be using less power, but at the end of the day, you see, I'm taking longer to heat up because I'm not giving it full burst at once. It's like I'm doing it, I'm adding it progressively, kidogo. This setup might be good if you're already at temperature, you see, because at the end of the day, I might not need that 1024 to heat up my. I might just need something low, some smaller value. So at the end of the day, I can end up saving power if I'm running on longer prints. But you see, with the bang, at the end of the day, you're maintaining a temperature. It's on and off. So yeah, I'm still maintaining that temperature. It's something that you need to actually get data and see which setup is best. But yeah, at the end of the day, you're just going to have resort to bang. But yeah, I'm still learning. So the target is 0. The PID value is initiating at 0. I mean, the target temperature is at 100. The PID is initiated at 0. From there on, now assigning pins, telling them that they are outputs. Like for the fan is an output, heater it's an output, LED it's an output, kill pin is an input, beeper it's an output. From there, okay, obviously you must initiate the communication, the serial communication. Hope you can see. Oh yeah. From there, print. This is now just to tell me my stuff is running. digital write. This to inform me if my serial printer is not yet on. I can still see that the thing has come on through the LED. This was for the beeper. I commented that out. The blink, even the light, the blinking function, I commented that out. At first, the PID thingy was to be a function. It does the processing. The only thing I just is call it and gives me values, but my function skills are not yet there. I'm not really sure. I'm not getting flowing values. It's as if this function is supposed to. How I know how to use a function is, for my setup currently, it's when my values are still, and you see at the moment the data is live, man. It's changing every moment, every second. So I just chucked it, took the whole code, made it structured. It's running straight. So this was for checking if the kill pin is run. That's the main function of this. If the kill pin is pressed, it will have some effect. Previous means this for the time for the derivation, because there's a change in time. My derivation is changing data over change in time. So new data minus previous data over new data's time minus previous data's time. I'm having an error, especially because I'm getting a big number, I'm getting an infinite. That means my changes, the temperature changes either as zeros, and because my change in time can't be that big. So at that time, maybe it was maybe I was having a faulty sensor. I don't want to do it because I still know it's okay. Just run it, we'll get an infinite. That's why even in one of my PID values, I was even trying to scale it down, like really down. I was multiplying it by 0.1, 2, 3, 4, 5, 6, 7, 8. 1 times 10 power negative 8. Tried as much. That number is big, but I'm not sure if it's the code. Mostly it's the code. It's always in the code. E equals to MC squared. Error equals to more code squared. Just need to know what I'm missing, what I haven't defined in my code, and add all. From there, I'm taking the values, the first values from the temp hotend, the sensor. It's converting. This is that function. It's from the library. It's storing them here, and then I'm creating an array to store the values, the temperature values for derivation, the current one and the previous one. So that's how it's two sides. The first value, obviously, it's the previous value, and then for time I didn't make an array. Makes me question, why am I even making an array? Can just cause I can. Okay, it's saving me space because I'm using one storage space for two datas. Okay, I'm not sure. Hit me in the comment there. The temp. This is for the second reading, which is 3 seconds later. I'm not really sure why I have this function of millis here for getting me difference in time, but yeah, I still just have it because it will give me the seconds, maybe the more precise labda, because I would have just put this in change instead of changing time, it being calculated. I've just set it straight to the 3 seconds. Second value stored in hotend temp 2, and then put it in the same array, temp array, but now in the second spot. So this array is now filled first spot, first temp, second spot, second temp. Alafu, since I'm doing a PID, you need to have an error. Like my target temperature is 100, but my sensors are reading 20 something. So my error is 20. No, my error is 80. That means working with errors is easier, rather, because you're working with a goal. You're working for the error to be 0. So that's why here temperature error, it's the target temperature minus the current temperature reading, the second one, not the first one, the current one, because this is the current one. So that error is what I'm working with. So from, as you saw in my PID values, it's checking for an error. It checks the error, does the computing. Once it says this is the right PID values, it gives it, sends it back to the loop feedback, and then waits for the other readings to know if what it added was a lot or was a little. This is now what's the PID is mostly just making the thing autonomous. So from the error you feed, you check the error, the computer readjusts its value. It might add or subtract depending on the position it is, and then it sends it back to the loop. The loop checks it again, finds the error again. In short, you're just working with the error. It's easier. From there, the integral, okay, there's the proportional. The proportional, it's already an error. It's not the actual value. It's the actual value minus the target value. Integral, I now see oh, I corrected it. I just took the value from above. I integrated the error. I was thinking I integrated it with respect to, I hadn't done the error thing. So I just took this value here, integrated it, just doing it power n plus 1 over n plus 1 plus c. So this is the c. This c, this integration constant, I'm planning to use the room temperature. Might work good, might not work good. Obviously it's something you're here to test, so I'm not sure what value to plug in there. Int temp, but room temperature seems like a reasonable value. So this might be constantly a 21 there, a 22. But let's check where we are at 20, yeah, 21, 22, 23. Int temp, hotend last. Is the integral. This is the last. Oh, you see now. I knew there was an error because I've figured something out. The last hot temp error, it's not the error. It's the actual error. I need to change this one. Let me check where I'm using it. Where do you see this word last? This is not like really lighted temp hot. Last time I haven't used it. I need to comment this still. Yeah. This line is currently unfunctional. Temp hot and last temp hot and yeah, there's no error. Hey, I need to comment. I just did comment it out, so you can just do it on. but it is not affecting the code anyway. So after getting in the integral, now I was going to the derivative. I started breaking it down. Originally it was just the whole function was one line, but since I was getting an infinite, I started breaking down the equation into parts. So this is the dx, the change in temperatures, the one stored in array 1, the current one, and the last one. I was thinking this is the last one that I was using here, but I updated after I updated. You know, with the code, once you update, just get coding. But once you update something, you might not update the whole thing. So that's the difference in temperature, and then there's the difference in time. According to me, that derivation looks okay. Which is now here, which the value is actually stored here. Should make these doubles, because making them ints is not doing justice to them. Let me just do that right now, because I can't make it from an int and then the master formula that's processing it as a double. It's just making, basically means I'm just feeding it how much of values. Sorry for that, I did a mistake. Okay, now the from there, now even this should be a double. Now this is the summation of the proportional derivative, proportional integral and the derivative part of it. The proportional plus times their proportionality constants. You see, this is the formula that I was telling you. So it's Kp times the proportional error, Ki times the proportional integral error. Yeah, there's an error. You see this is an error. It's supposed to be an error. It's not an error. I already did it. It's target temp minus array temp, so it's okay. Target temp minus. I'm already computing the errors. So I was thinking I was not computing the errors. Okay, so once you're fed in your proportionally your values, you sum them up. Now from there, this is the kill pin again. It's checking. The whole function will still be checked. The thing here was closing here. The function for the kill pin was closing here. See, so it won't do anything. It will do this part, but it won't feed. From this point on is where now I'm feeding values to the hotend, to the temperature probes. Not to the probe now. It will kill everything below it. Then, in short, this is the hot part. In short, the rest are just some computation and initialization. Kill pin ends. No need for me to explain that, because I think the end of the day I checked it. No, it's still there. Now from there, if hot temp is less than target temp, now this is the condition, the main condition. This is the main bang condition. So you see, if I'm using an analog setup to try to chase to push the temperatures, at the end of the day it still has to be a digital, because once it gets to temperature, it cuts. And then the other function was the PID. I didn't want the PID value. This value can go past 1000. There's no harm to it, because it has already gone past 1000. But I think by default the Arduino will know 1000 is maximum. So if it's less than 1000, it will keep adding, and the temperature is still low, it will keep adding to that tens. There was a period I was subtracting. Now this on adding. Once it gets to temp, I can't. There are two options. Either I maintain it at there, or I reduce it. I'm using at the end of the day, I just found I'm using, it's a form of bang bang. From here, once it gets to 1000, it goes to 1000, it checks it's 1000, it skips this, comes here. After it's done this, it subtracts 10, so the value comes back to 990. So this condition will be true, so it will say it's okay. Do the PID values that the computer has already, what you have set it, you yourself, you set it to the proportionality constants, the Ki, the Kp, and the Kd. But from there on, it's the comp's work to do it now. It will check, it will set the PID value for you, and then the fan pin was set at 100. It was not running. It was not running fast. Suppose highest it's. That's why you see they are on analog writes. When you go to the test code, all of these are digital writes. They just saying low or high. Can I have closed it? Don't open it. But if you have an analog write, you can push 0 to obviously to 10, 1000. So yeah, gets to 990. This part here is to reduce the PID value by 10, so it goes to 990. That's just basically it. The rest of it, this is a copy of this. It's controlling the hotend by feeding in the PID values. So you see, even this PID temp, I'm not still using it. This at the moment, the PID values, I'm still experimenting on them, so I'm not using this value anyway. I'm not feeding it on the computer. Currently I'm still running on raw temperature values. But if I was using these PID values, if my derivative wasn't as infinite as it is, here it will be checking, instead of checking temp hotend, it will be checking PID temp. Now the good thing with this, like kwanza in that proportionality part of it, I can say it has a scale of 20. So my temperature can be, to a scale of 20 can be big. Let me say a scale of 2. My temperature can be 10, but I'm telling it, the computer is reading a temperature of 20. This comes handy, especially when you're getting close to your value. It speeds you up, getting you closer to your value, or something like that. But it's proportional. It doesn't do anything. The proportionality constant just follows your value. The integral part is what determines by how much you want it to achieve your value, how fast or how slow you want it to achieve. Rather, it's mostly used as the damping. So the integral and the derivative are the damping ones, but the integration follows your value. Rather, it partly follows your value, because even if you look at an integration formula, you're basically integrating your value. So yeah, it's roughly the same as proportional, but it will tell you. You can say the time up of your the period, faster or slower, for it to the proportion. And then the derivative is what checks at changes, slight changes, any spikes. The derivative part of it is good for it. So the derivative part will come mostly handy when it's starting and when it's switching on and on. It's good for spikes. It doesn't follow per se the value. It checks the difference between the value, the current value, and the previous value. It's working on that, and then based on that time. So that you get e value, the previous value, and the time it was taken, and then this value and the time it's taken, and then the difference between the values and the time. That's the derivative. You see, it has a rate part of it. it checks, in short, just know it checks for spikes, any sudden movements, any sudden changes. That's what I can say. I haven't given you the best description of the PIDs yet. I don't want to. Should I run the code? Let's just run it because let me see if there's an error. No, there's no error because I have no keyboard attached. But from how it's running, let's see if there's an error. Oh, it's done compiling. Good. We can upload it. I wasn't running the code because the value was giving me wrong. So at this, my serial port is still running. It's uploaded. Now we can start. It will just give me the same values. When it freezes there, it's giving me a wrong value, so it will automatically jump off the loop. So from there, you see my now let me give you what these values actually mean. Let me just, so it stops refreshing. So here I am, hotend temp. So temp 1, previous temp. This is the raw value. These two values are the values from the array. So this is the previous temp, this is the current temp. This one, this is not. This is 0 and this is 1. So the difference will be between these two values. And then oh, I'm getting a degs. Now from there, there is PWM hotend. This is the raw PWM value that's been fed. It adds up by 10. So like the next one should be that 60 or 60, yeah, E60, and then checked temperature is Africa. So if your power supply is not on, this thing will go up to 1000. Still checking if it's adding power, but in actual sense, it's not adding the actual power. It's adding to it, inaongezea, but nguvu yenye iko nayo, it's not the maximum power you're feeding it. Obviously it will be capped at, currently the power supply is off, so my main feed is from the arduino, is from the computer. That's a 5 volt, and roughly I don't want to approximate my amp at 1. That's a lot. Amp of maybe 0.1. So that's 0.5 amps watts. See, that thing can't heat up anything. But from the code side of it, it will still add the PWM values. But if you power on the power supply when the PWM values are high, it will instantly go high. So yeah, that was that. So the PWM values, and then hotend. So from there, hotend PID. So PID temp. Currently it's not available because it's a really big number. Let me explain to you why. The proportionality. This is the proportion. I wonder why I'm getting a 77, and I haven't done any Why is it a 77? Temp content proportional error. Oh yeah, it's error. Sorry. So this, I'm currently at 20 something, 23, 21 point something, but my target is 100, so 70 something. And then you integrate this value up here, becomes something big, roughly becomes big. And then there's now the derivative. You see, I'm getting an infinite. Now I took apart the millis function can't compute seconds. That's simple. Kumbe ilikuwa, by the way, I'm getting an infinite, I'm not getting an error. Infinite comes when you get it divided by 0. I was thinking it was 0 divided by something. So the problem is the function in the Arduino code, this function that I'm using. I need to go now, get something, grab something, smoke up, and then come check up this millis function. This is what I'm using. I think I'll change to micros. I had some place micros. You see, the problem is this is a timestamp. Hours, minutes, seconds, microseconds. This thing goes to 1,000th of a microsecond. The last time I checked computing this stuff, it doesn't compute the seconds. It computes this. But let me check the difference in time. This, oh, sorry, I was thinking. I need to print out the values for the time. I'll come do that. Okay, but I'll come do that later. The video is getting quite long. So 0, hotend, infinite. So my problem you have established is time. Need a proper functioning for subtracting time, and then yeah, that's it. Start again. So yeah, that's my rundown for my hotend test. It's not yet complete, still a work in progress. I'll now need to come sit down. There's a log I saved. I might just do it for the fans. Let's see, let's run it. Let me turn the power supply on. You see, it's feeding. I have a lot of delays. That's the other thing. There's another delay. There's a delay here, and there's a delay here. So the total delay, since these two delays are separate, the total delay is 4 seconds. This 1 second here, and the second between the readings. That's why I wanted it to become a function. You see, if it was a function, these 3 seconds will be done separately. That was my main idea when I wanted it to be a function, but the functioning part of it disturbed me, so I have this. That's why I have this lag. See, it's updating every, I don't know if it's 4 seconds or it's 3 seconds. So let's check. Okay, focus on the Casio. One. Is it that my camera is bad? The screen of this thing has too much glare. Yeah. Every 4 seconds. Okay. From there, yeah, let me switch on the power supply and we start viewing. Everything is powered up. My array is starting to huh? Oh, sorry, it's not connected. I was moving it. These abrupt connections are the ones that are most complicated and dangerous. Okay, hope we don't burn anything. Okay, we are heated up. 72, that area is smaller. 62, 10-degree difference. What's my PID value? 1000. I'm at full lamp. I'm at full power. Let's see how long it will take for it to get to. I'm already at target temperature. You see, from there it will stop. If it stops, one thing is good. We know we are not feeding any more power. The PID is stopped. This is another proper definition of E equals to MC squared, because this is a form of error. It's supposed to kill itself. It's supposed to kill itself automatically. Let me switch off before things go off. I can't see anything above 100, because after 100 the statement becomes false, so it doesn't view it anymore. So that's the rundown for today. Hope you found something interesting, something worthwhile.